Up next, the future of AI research, open weight models and new paradigms, moderated by Amy Nordrum, Executive Editor of Operations at MIT Technology Review. Please welcome our panelists. David Stout, CEO of WebAI. Dr. Tom Mitchell, Founders University Professor in the School of Computer Science at Carnegie Mellon University. And Dr. Jack Wells, Director of Higher Education and Research Computing at NVIDIA.
Hello, everyone. It's great to be here today with all of you talking about the future of artificial intelligence. My name is Amy Nordrum. I'm an executive editor at MIT Technology Review. Given the topic of today's summit and where we are here in DC, we want to focus our discussion in these next 30 minutes on how new research advances in AI could impact the usefulness of this technology for scientific discovery, and what decisions we make about how to govern and deploy it might mean for scientists. What does scientific progress require of this tool? Must it be open source and its workings knowable? Are the AI systems we have today really capable of delivering novel results or aiding scientific progress? What would make them even better at this? And what's the role of universities or public institutions in setting this agenda, given how dominant corporate R&D labs have become in the space? These are the few of the questions that we're going to attempt to tackle in the time that we have here. So Jack, I'm going to begin with you. Generative AI is, of course, the hot new thing right now, but machine learning, computer vision have been around in the sciences for decades. Just set the stage by telling us, how do you think about the value of all of these different types of artificial intelligence to the sciences?
Thanks, Amy, and thanks to the organizers for the opportunity to participate. Of course, machine learning, AI, is a topic that dates from the 50s. I think it was largely being propagated in the engineering disciplines. In my experience, I think all that I learned in my early years of doing research was through an engineering collaboration. Only a few scientific groups were engaged in these ideas. But the big change really happened with image classification. I think of the ImageNet competition and AlexNet as a major breakthrough as we look back that demonstrate deep learning neural networks could have a huge impact. Who would think that over-parameterization of function approximation would be so useful? It's really a tremendous progress. We know that there are many applications of machine learning and reinforcement learning in robotics and automation, and of course, tremendous progress in natural language processing. The paper, attention is all you need, and the ideas of generative AI have really exploded now, leading to so much variation. I think it's still the early days, but you're starting to see these ideas now applied in the domain sciences with new data sets, and the progress is really fast.
Well, Tom, speaking of generative AI, we're a few years in now to this whole generative AI experiment. So where, in your view, has artificial intelligence and generative AI in particular had the most impact within the sciences, and where has it fallen short?
Well, I think we've heard a lot today about some of the successes, in particular biology, material science, even weather forecasting. These are areas where the common theme is really that people were able to get together reliable large data sets and then use machine learning to train models on those. If you look for the failures, for me, one of the failures is neuroscience. Why do we not see comparable panels discussing the advances in neuroscience? And I think the reason there is really around the data, and it's twofold. One is, in neuroscience, the data is not so homogeneous, not so uniform. We have data at the cell level, we have fMRI images at the whole brain level, and this data is not particularly uniformly documented. So there's that issue. The second issue is a cultural one. The culture of neuroscience is to protect your data and not share it. which of course works against this. So I think there are some examples and successes and failures, and maybe some lessons to learn from.
That's a fascinating example. I want to talk with you more about that in a bit. But first, David, your turn. Your company is pretty squarely focused these days on generative AI. When you think about generative AI as a tool for the sciences, do you see greater potential in using it for discovery and theoretical advances, or practical experimentation, or something else, and why?
Yeah, thanks for having me. And I think when we think about AI used for science directly in research, there's a lot of exciting things, and I think people tend to migrate towards the discovery piece because that's maybe the most exciting. But I think there's a lot of practical ways to leverage AI today in ways that we just haven't with maybe some of these foundational models, right? Where what we're seeing is this advent of hyper-contextualized systems living in data environments where traditionally you just didn't have a foundational model living or having access to for compliance reasons, or maybe just from an IP perspective, they didn't want that data going offline anywhere. And what we're seeing is companies just connect these really large data pools and data sources to series of contextual models that maybe are, for the sake of example, maybe one model is contextually very, very rich in research area, like in vaccine creation. It gets exposed to this large corpus of data that this organization has, and it's not thinking about anything other than new medication and new treatment options and new formulas, and all of that discovery that comes from that can then be compounded by a model that's also having access to that same data source, tasked with a totally different mode of operation. And there's a lot of people talking about agents and things like that, but this isn't an agent system. What we're seeing a lot of enterprises do, both private and public sector do, is lean into this idea of contextual experts operating independently. They're not like handing things off to each other, but they're coming to conclusions collaboratively. And we're seeing this across discovery. I think that's where a lot of clients want to go, to be honest, to start. But often where we land in some of the most valuable practical applications are optimizing existing discoveries. And there's a lot more to do with things that we already have and we know have clear pathways to work. But there's a lot of optimization to be done. There's things that we're working on with biotech and pharma that are pretty exciting that I can't particularly talk about, but things soon that will be talked about that are just improvements on the existing status quo.
Intriguing. Please let me know and you can tell me more about that. Okay, Tom, back to you. I want to follow up on your point about neuroscience as well. You had a story actually about training a foundation model for the brain that I think illustrated some of the challenges of approaching some of these problems, at least from within a university. So can you briefly tell us that story?
Sure. So we are thinking about pulling together the brain image data that's available in public domain and training a foundational model on that. In analogy with the model with ChatGPT, which was trained, given this sequence of word tokens, predict the next word. Instead, we could say, given this sequence of brain images and stimuli given to the person, predict the next brain image. And the idea here, of course, is that in analogy with ChatGPT, which was forced by its need to do that training to come up with very sophisticated representations of the meaning of those earlier words so that it could predict the next one. This would force a system to do a comparable thing, to come up with sophisticated representations of the time series of neural activity. I think this is a good thing to do, and I've been talking with a number of people across the community about it. people think it's a reasonable thing to do. But the problem really is getting together the data. And it turns out NSF tried on multiple occasions to fund centers that would pull together exactly this kind of brain image data. First at Dartmouth in the 2000s, and then later, 10 years later or so. Both of those efforts failed. And those efforts failed in part because we did not have good standards for representing the data and the conditions, the exact conditions under which it was captured. So I think, again, that's the lesson from those earlier NSF ones is that getting that data together is tough. I think if we could do it, the potential for training such a model is very interesting. And I just want to point out in closing that when we talk about AI in science, if you talk about, for example, AI material science, you can see the role of AI is to be a modeler, a data analyst. But when we talk about neuroscience and AI, the relationship between these two fields very different because AI is about processes that create intelligence. And brains are processes that create intelligence. And so there's an opportunity at the intersection of these two fields to have a jointly developed science of intelligence that leverages off what we learn from artificial systems and what we learn from natural neural systems.
And Jack, you've been involved in a lot of public-private partnerships and academic collaborations. I'm curious for your take on that. Like, what is key to making those kinds of relationships work? And what are the characteristics of the ones that you've seen, particularly regarding AI and science, that have done well?
So thanks for the question. Public-private partnerships, in my experience, are something that is relatively new in our science ecosystem in the US. And I think we're still learning. The one I've been involved in very much in the last 18 months has already been mentioned, the NAIR pilot. NVIDIA made a $30 million in-kind contribution to that. And I participate on the monthly public-private resource providers call, resourcing our capabilities for the users that NSF assigns. So it's been very interesting. Of course, this is a pilot that was supported through an executive order. It was not yet fully funded. And so it's been a best effort. Colleagues from the federally funded institutions are basically working two jobs as they try to execute this because they're working the job that they've been given and that is fully funded, and this pilot as an executive order was coming on top of that. So they're working heroically. We're giving best effort also to try to help prove the concept that public investment in computing infrastructure for AI is important and valuable. So I think a lot of conversation is needed in terms of best efforts. We'll get better at this as we practice, I will say. It's important from, I think, industry's perspective to understand, to value industry's in-kind contribution. Often that is the most valuable thing that we have to offer is our technology and our people. And so it's important that that be valued. I think the private sector cannot replace the public sector, but we can work together effectively going forward.
So Jack touched on some of the funding and personnel challenges here. David, I'm curious, what are some of the technical hurdles that you see as most significant still for scientists who are eager to work with AI to overcome?
Yeah, I think that there could be a slight misconception that an API is solving every problem for AI. And I hear more groups that I meet with that have been engaging with Gen AI for maybe a year, maybe longer, and it's not solving the problem in the way they anticipated to solve it. And one of the big issues here is that there is a massive talent gap between the companies producing AI and working with AI, and then the companies that would like to leverage it, which is obviously accountable for part of that. But also, I think this idea of like a one-size-fits-all turns out to not be as true as one would like to claim it being. There's a lot of physical limitations, and I appreciate all the neuroscience conversations here, because neurologically, there's really no representation of one mind being a singularity. One of my old professors used to say, the human mind can learn anything, but it can't learn everything. And yet, there's a lot of tools today that are trying to promise that and say, like, prompt engineer your way to success. What we're finding is what's actually working in making its way into production is a distributed approach to AI, where we're saying we're going to load balance 100 unique models, and we're going to mimic a civilization pattern where this room is full of uniquely brilliant people in different ways in different areas, and a singular human has not really done a super intelligent thing, but civilizations and groups of people have. And I think we're in this new era now that we're getting into an integration era, and we're expecting outcomes. And I think the paradigm is drastically going to change, and the expectations are going to change with that. We see a lot of tools that are succeeding, but those tools are not succeeding in like mission critical tasks. And that's one of the challenges I'm seeing almost every day. Is this is great for customer support. This is not great for maintaining an aircraft.
Yeah, makes sense. Tom, I want to ask you for your views on open source versus closed source. So what's your opinion on the matter of keeping models and their weights open versus closed for proprietary reasons? And then despite your own view, what do you think is the most likely outcome, and how will that impact scientists who are working across these many models?
Well, I think open source models are going to be very important, especially at the intersection of AI and science, because we want these models to be published and used by the scientific community the same way that we publish equations. In fact, you can almost think of many of these models as fulfilling the same role as F equals ma, except that instead of having 3 variables that it explains the relationship among, in the case of a virtual cell, for example, it'll be explaining the relationships among tens of thousands of variables. But it'll be a similar kind of role. We'll want, as scientists, to use these models the same way we do use equations to predict values of some things from the other things that we can observe. So that argues pretty strongly for open source and for being able to run them locally, modify, experiment with them, and so forth. I do worry about, in fact, I asked this question privately after the earlier panel that we had here on biology, AI and biology. I worry that if we're in a world where the best way to get reliable data is to form a company, get it funded, and create that data yourself, then who will get to use that data? And in private conversations after the panel, it seemed like the consensus was the company will own the data, and if you want data, you have to start your own company. So I worry we're in a world where we're talking about open source models, but I think there's a corresponding question about open source data. And even if it's public-private partnerships, who's going to get to use that data?
And Jack, I saw you nodding as Tom was advocating for open source. Are there any risks or challenges that would come up if everything was open that scientists specifically were using?
Well, yes, thanks for giving me a chance to speak to this. I think from a perspective of the philosophy of science, reproducibility is fundamental. And so from reproducibility, you can go to transparency, the openness of tools and methods, and you find yourself concluding, I think, that the open models and open weights, open data is really the only approach that's fully consistent with science. Now, the values of science are not the only values we have to balance, to be sure. But from a scientific perspective, we need those things for sure. There are challenges. We have a lot of data being produced by our scientific instruments today, for example, in federally funded institutions. But the programs that were put in place did not originate with the end in mind of providing massive data. And so now either the work has to be done to compose that data in a way that it can be used, or just begin again. And I think different programs will make different choices. If you're in a national security program and the data you have is irreplaceable, for example, at some of our national security labs, then you will do the work that makes that available for AI. But in some of the other data sources that have high throughput data available now, I'm not sure the old data will be recovered for use in AI. People may just think about the future, instrument their experimental apparatus for this purpose, and go forward and collect data. So I think we should be asking really good questions about data availability as we think about this, the AI triad of data, compute, and algorithms and talent. If the data is available and freely available, we should be able to open up our laptops and get to it.
And David, you work with a lot of companies that are perhaps hoarding some valuable data for scientists and might not be so interested in being so transparent and open. It's just not within their interests. Is there a role for academic collaborations there, and how would that work?
I think there has to be. Yes, there are groups we work with that don't want to release their data, and that's their, in their interest. It's also at times in the interest of the public to not release the data. So there's a time and a place to have open data, and I think there's an issue that we're talking around when it comes to data. And one, it's fundamental to have good data to build these models, but today we have no protocol or practice in ownership. And when I think of modeling in particular, I think of it as like we're in this book era of AI. We're not in the information era, and a lot of people are trying to push us forward as if we're in this information era of AI. We're really in the publishing era of publishing books. And what's required to actually publish a model? Like the data around it. It needs to be referenceable. It needs to be citable. We need to have real processes in place when we publish an author, right? And we know that this is a resource that people can leverage as a true knowledge base, just like a book. We've taught people for a very long time with books, and AI is going to be a mechanism like that. So in order to do that, there's going to need to be data that's referenceable. But what do we do with the creators of the data? And our scientists, our contributors, there is no structure in place for them. We just want to take this data from these companies that have spent decades building it, that's valuable, it's hard work, and there's intellect required to make that data. And we can't just demand it. There needs to be a process in place for authors to be rewarded for contributing. There is no ecosystem like that. So WebAI is working with Anaconda and some other groups to try to think of how can we do this? At a very high level today, we're very early, but we're talking with universities, and how can we create a space where contributors can be incentivized, one, to contribute, but not totally left behind, because you don't want to publish a paper and then just have AI train on it and blot you out. That's not why people go into research, and that's not why they wake up every morning and contribute. They want to make a difference. So,
yeah. Well, for the time we have left, I want to ask each of you to look ahead to the future of artificial intelligence and scientific research. Where do you see things heading from here with AI? What kinds of new advances or capabilities are on the horizon that those who are working on applying artificial intelligence to the sciences ought to be aware of or looking out for? And Jack, I'll begin with you.
Well, the first thing that comes to my mind is on this data theme, I guess because we've been talking about it. But the communities that have their data already well organized, because that's the way they've always worked, that's where we should expect to see the most rapid progress. And other areas where the data is not available, as Tom has indicated, where communities haven't already sorted through many of these problems, there's work to be done, and progress won't be as fast there. So if you're thinking about the fast starters, climate and weather have been mentioned, that's consistent with that idea, that the weather data is very available and it's being applied. And there are other areas, biology, it's already been, the databases for biology. Communities have sorted through this. It's often been in domains that do not have a partial differential equation at the core of them. So they've had to deal with the data in a way that some other disciplines haven't had to deal with. The fast starters are going to be the ones that have their data organized. That's my contribution.
And David, same question to you. What's on the horizon for advances in AI that those who are working on applying it to the sciences ought to know about?
Yeah, I think we're going to see an advent of model proliferation, and the choice of model is going to become astronomical. And in somewhat, in this process, you're going to see the commoditization of a model, but you're also going to see a rich library of sorts of models that, thinking about what you were talking about with the neural representation, that's going to be a very bespoke model, right? That's not your general purpose model. It's not going to write a poem about frogs unless you think it will. But what it will do is it will predict the next image or neural activity. And similarly, I think we're going to see this advent of incredible choice in modeling. And the most exciting thing I see happening is what happens when those models talk, and what happens when we throw those models at really hard problems, and what kind of outcomes are we going to see. And I think it's going to be incredible, and it's almost unfathomable.
Fascinating. Okay, Tom, you've had the most time to think, so you must have the best answer. No pressure.
Well, I'm going to look further into the future. I'm looking forward to the day when we have these different models for different types of sciences communicating with each other to become more interdisciplinary. So, for example, think environmental modeling, and imagine you have today's even weather forecasting system with a model that's predicting responses to drought conditions in different places. And I think one thing that eventually we'll get to is the sciences deciding that there are bigger problems that are multidisciplinary, and we need these models to communicate with one another. So we should aspire to that.
Mm-hmm. And this question I'll open to anyone who would like to contribute an answer here. I've heard more critical views lately that other research directions in artificial intelligence are being underfunded because of all the attention on generative AI. So do you think that's true? And if so, where would you like to see more attention go within the AI research space? Anyone who has a thought there?
Well, I'll just say, I think that when it comes to university research in AI, we're in for turmoil. We're already in turmoil, but it's going to be more turmoil for the coming years because computer science departments in universities in the US used to rule the roost and be the innovators of nearly all advances in AI. If you've noticed in the past 5 years, that's no longer the case, and it's hard to imagine it coming back. So I think that what we're likely to see is AI and science being a great thing for universities in just about every department, and this will be a great decade for universities because of that, because every discipline will get a chance to reinvent itself with AI tools. And the one department that's going to have the hardest time is probably computer science and AI.
I thought you were going to say neuroscience. Well, I really appreciate the conversation today, Jack, Tom, and David. Thank you for being here, and thank you all for listening.